Venus, the second planet from the Sun and Earth's nearest planetary neighbor, is an oddity in many ways. The hot, hellish planet spins backward and might even host life in its impenetrable clouds. In the early years of the space age, astronomers' knowledge of Venus was very scarce. In fact, they were limited by the most general of facts, such as the planet is slightly smaller than Earth in size, and its surface is constantly hidden by thick clouds. What is under them remains the subject of much speculation. But today, we've got something truly extraordinary, never before seen: photos of Venus, unveiled by none other than world-renowned physicist Michio Kaku.
Venus is this oddball planet, this evil twin of the planet Earth that is so hot, much hotter than it should be. Desolate, but maybe a future home for the human race.
Notably, these shocking photos were originally taken by the Soviet Union many years ago, and they were kept hidden from the public eye until now. But why was that? Why did they keep these photos under wraps? Is there a terrible secret hidden in those 40-year-old photographs? Join us today as we dig deep into declassified photos from Venus by the Soviet Union, which is panicking Michio Kaku. If you ventured outside after sunset recently and happened to glance to the west, you may have noticed an astonishingly bright star glaring down on you, seemingly hovering in the sky. Is it a helicopter, a supernova, or a UFO? Nope, that's Venus, the second rock from the Sun, Earth's evil twin and frequent UFO impersonator. If you haven't seen the planet before, right now is the best time to take a gander. It's not hard to spot. Go out when the sky is getting dark and look west and then up. Venus is incredibly bright, shockingly so at times, which is why it's commonly mistaken for an unidentified flying object. Named for the Roman goddess of love and fertility, Venus, as famous physicist Michio Kaku said, is one of the nighttime sky's most beautiful sights. It is the sixth largest planet in our solar system and is sometimes referred to as Earth's twin, as the pair are similar in size and density. But don't be fooled, they are far from identical and are radically different in almost every other aspect. Up close, Venus smells like rotting eggs. Further observations of Venus in the space age show a very hellish environment. According to Michio Kaku, he said, Venus is so hot, much hotter than it should be. It is well known as the hottest planet in the solar system. But why Venus is the hottest planet in the solar system is rather complicated. Although Venus is not the planet closest to the Sun, its dense atmosphere traps heat in a runaway version of a greenhouse effect that we will see firsthand on Earth with global warming. As a result, temperatures on Venus reach 880 degrees Fahrenheit, that's 471 degrees Celsius, which is more than hot enough to melt lead. Spacecraft have survived only a few hours after landing on the planet before being destroyed. With scorching temperatures like this, Venus also has a hellish atmosphere that consists mainly of carbon dioxide with clouds of sulfuric acid and only a trace amounts of water. The atmosphere of Venus is heavier than that of any other planet, leading to a surface pressure that's over 90 times that of Earth, similar to the pressure that exists 3,300 feet or 1,000 meters deep in the ocean. Venus's surface is extremely dry as well. During the planet's evolution, ultraviolet rays from the sun evaporated water quickly, keeping Venus in a prolonged molten state. There is no liquid water on its surface today because the scorching heat created by its ozone-filled atmosphere would cause water to immediately boil away. Roughly 2/3 of the Venusian surface is covered by flat, smooth plains that are marred by thousands of volcanoes, some of which are still active today, ranging from about 0.5 to 150 miles or 0.8 to 240 kilometers wide, with lava flows carving long, winding canals that are up to more than 3,000 miles. That's 5,000 kilometers in length. 6 mountainous regions make up about 1/3 of the Venusian surface. One mountain range, called Maxwell, is about 540 miles, 870 kilometers long, and reaches up to some 7 miles, that's 11.3 kilometers high, making it the highest feature on the planet. Venus also possesses several surface features that are unlike anything on Earth. For example, Venus has coronae, or crowns, ring-like structures that range from roughly 95 to 1,300 miles, 155 to 2,100 kilometers wide. And scientists believe these formed when hot material beneath the planet's crust rose, warping the planet's surface. Venus also has tesserae, or tiles, raised areas in which many ridges and valleys have formed in different directions. Venus has no known moons, which makes it nearly unique in our solar system. The only other designated planet without moons is Mercury, which is quite close to the Sun. Scientists aren't yet sure why some planets have moons and some do not, but what they can say is that each planet has a unique and complex history, and that may in part contribute to how many moons are formed or didn't form. Regardless, one thing is for sure: Venus is a very difficult planet to observe from up close because spacecraft do not survive long on its surface. Indeed, Mikio Kaku even drew a scenario as bad as hell once humans set foot on the evil planet.
It would crush you. So an astronaut walking on Venus would first sink into the molten surface, be crushed by the atmosphere, and then burned alive by sulfuric acid rains. So Venus is the least hospitable planet in the solar system.
That's also why, while you can find dozens, if not hundreds of images of Mars' surface, Earth's other neighbor, Venus, is limited to a series of images taken in the early 1980s. Furthermore, those images weren't even taken by a NASA spacecraft, as NASA has yet to land a spacecraft on the planet's surface. Instead, the only photos of Venus' surface we have to look at were captured by Soviet-era spacecraft over 40 years ago. Venera was a series of satellites launched by the Soviet Union in the 1970s and 1980s to study Venus's environment. It was also the program aimed at returning the first close-ups of the surface of another planet. Over the course of the program, 13 probes successfully reached Venus and transmitted data about our neighbor. 8 landed successfully on the surface, and 4 returned pretty outstanding photos. Venera 7, the first orbiter spacecraft with a lander in tow, launched on August 17, 1970. After a 4-month transit to Venus, the landing probe separated the orbiter on December 15th and plunged into Venus's thick atmosphere. After a period of aerodynamic braking, the upper hatch and heat shield released, exposing the spacecraft to Venus's elements and releasing the parachute that slowed the lander. The chute was released 6 minutes later. Venus's atmosphere was enough to slow the lander for the final 29 minutes of its descent. It landed successfully, and data was transmitted from the surface for 1 second before the signal failed. But post-flight analysis of the recorded radio signal revealed that the probe had actually transmitted data for 23 minutes before succumbing to Venus's environment. Venera 8 followed, launching on March 27, 1972. It reached Venus on July 22, 1972, and once it reached the surface, it sent back data for 63 minutes. Venera 9, which launched on June 8, 1975, was the first mission to attempt to take pictures of the Venus surface. Though the probe landed in good health on October 22nd, only one of the lens cap on the 2 cameras separated. What was planned as a 360-degree panorama around the lander became just a 180-degree image. Venera 10 followed in Venera 9's footsteps, reaching the surface on October the 25th of 1975. Again, only one of the lens caps separated, properly returning a 180-degree panoramic image before going silent after 65 minutes on the surface. And those are the first ever black and white panoramas of the planet. Interestingly, before some scientists had suggested that due to the enormous pressures on the surface, there would be an effect of such powerful refraction that all Venera landers would be able to photograph themselves. According to another opinion, the surface of the planet could be completely hidden by a haze. However, it turns out to be much easier. In the images of Venera 9, scientists saw an area covered with numerous stones with sharp edges. The panorama of Venera 10 showed formations similar to floods of solid lava. No dust, fog, or refraction effect was found in the atmosphere of the planet. The next two missions were partially successes. Venera 11 landed on December the 25th, and Venera 12 landed on December the 21st, both in 1978. But in both these cases, the lens cap issue struck again. On these two missions, both lens caps on the cameras failed to separate. So, while the landers returned data, neither was able to image the surface in 360-degree views. Venera 13 launched on October the 30th, 1981, and landed on Venus on March the 1st, 1982. Once on the surface, the cameras began taking a panorama around the lander. The spacecraft survived for 127 minutes before going silent. Venera 14 was the last lander mission on Venus. It launched on November the 4th, 1981, and landed on March the 5th, 1982. The lander survived for 57 minutes before falling silent. So, the images from the surface of Venus might not be as stunning as the vistas we have from Mars, but when you think about the environment those landers had to survive on to take those images, temperatures approaching 900 degrees Fahrenheit, and an atmospheric pressure 92 times what we feel on Earth, they become pretty incredible. And though today's Venus is grotesque, there have been a few tantalizing hints that billions of years ago, Venus might have been more akin to Earth's twin. In addition to their comparable sizes, the worlds also formed close together, which suggests that they are made out of the same bulk of materials. The big difference is their proximity to the Sun. Because Venus is roughly 41 million kilometers closer, it receives twice as much sunlight as Earth. But a few billion years ago, a slightly fainter sun might have allowed for a relatively cool Venus, one where liquid water could have pooled in vast oceans that were friendly to life. A new study recently accepted in Geophysical Research Letters suggests that not only was Venus habitable in the distant past, it could have remained habitable for billions of years. Michael Way from NASA's Goddard Institute for Space Studies and his colleagues applied the first three-dimensional climate model, the same computer simulations used to predict human-caused climate change on Earth, to early Venus. Because previous research only looked at one-dimensional climate models on Venus, which consider incoming and outgoing radiation but do not visualize the complexities like clouds within an atmosphere, the results are a huge step forward compared with previous studies, scientists say. There's a real difference between a back-of-the-envelope calculation and actually plugging it into a more sophisticated model, said Jason Barnes, an astronomer from the University of Idaho, who was not involved in the study. The team first simulated how the Venusian climate might have looked 2.9 billion years ago. Such an ancient date required the researchers to make a few educated guesses about the early planet, such as assuming it had a shallow ocean, just 10% the volume of that on Earth today. But the results were clear. 2.9 billion years ago, the second rock from the Sun could have had a balmy Earth-like temperature that hovered around 11 degrees Celsius. The team then ran the model for a later Venus some 715 million years ago and found that even under the site's heightened heat, the planet would have warmed by only 4 degrees Celsius since the earlier time. Such a slight increase in temperature would have allowed the planet's liquid ocean to persist for billions of years. What allowed Venus to stay wet for so long? According to the models, clouds played a key role. They likely piled up on the day side of the planet, acting as a bright shield that reflects incoming sunlight, and never formed on the night side, letting heat radiate off into space. To me, the real takeaway message is that Venus could have been habitable for a significant period of time, and time is one of the key ingredients to being able to originate life on a planet, says Lori Glaze, an astronomer at NASA Goddard Space Flight Center, who was not involved in the study. This suggestion adds a new element to the question of habitability, time. Habitability is not something that's static, says David Grinspoon, an astronomer from the Planetary Science Institute and a co-author of the paper. It's not a question of a point in space. It's a point in space and time and how long a planet could potentially retain oceans, and if that's long enough to be considered a good candidate to have an origin and evolution of life, Grinspoon said. Those cool conditions, however, depend on whether Venus looked the same in its youth as it does today. Although the researchers added an ocean, they kept Venus's present-day topography intact, and whether it has always spun as slowly as it does now, taking 243 Earth days to complete a single rotation. Because the answers to both questions are fairly uncertain, the research team also modeled what Venus's climate would have looked like 2.9 billion years ago if it had an Earth-like topography or spun at a slightly faster pace. The differences were huge. With mountain ranges and ocean basins similar to Earth's, the temperature was 12 degrees warmer than with Venus's topography. And if the rotation rate was 16 Earth days, the temperature skyrocketed to 45 degrees higher than the level with its current rotation rate. The cloud pattern that kept the climate cool only formed if the planet was rotating sluggishly. This result has vast implications for the world of exoplanets. The community should be careful about ignoring worlds that are very close to their stars, like Venus-type worlds, Way says. If a few key characteristics, such as an exoplanet's topography and rotation rate, are just right, then the inner edge of the habitable zone, the regions in a solar system where conditions conducive to life can arise, will be closer to the host star than is usually thought. The finding is especially important given that these close-in worlds are much easier to observe and characterize than any other types of planets. The much-anticipated James Webb Space Telescope, the JWST, often referred to as Hubble's successor, for example, will likely only study worlds that hug their host stars, making observations of planets with wider orbits like Mars or even Earth out of the question. Or, as Ravi Kopparapu, an astronomer at the Pennsylvania State University, puts it, the closest to Earth we can get with the James Webb Space Telescope is Venus around cool stars. But Glaze could not consider her excitement about the latest study because of the light it sheds on a rock back home. Venus is the planet next door, the sister next door, and it's so surprising how little we know, she says. We know Mars so much better than we do Venus. Those, plus Earth, are our 3 terrestrial planets in our own backyard. If we don't understand those 3 planets and what makes them the same and what makes them different, we're going to be hard-pressed to interpret the new planets that we're discovering outside our own solar system. There is still more important data that we need to collect in order to put tighter constraints on these models, and we have the ability to collect those data now. We just need the missions, Glaze says. And just as expected, in the latest announcements from NASA's Solar System Exploration Program, 2 missions have been given the go-ahead, and they're both bound for Venus. The 2 ambitious missions will launch between 2028 and 2030. This marks a considerable change in direction for NASA's Planetary Science Division, which hasn't sent a mission to the planet since 1990. It's exciting news for space scientists and space lovers like us as well. The first of the 2 selected NASA missions will be known as Da Vinci Plus, a shortening of Deep Atmosphere of Venus Investigations of Noble Gases, Chemistry and Imaging, or again the acronym Da Vinci Plus. It includes a descent probe, meaning it will be dropped through the atmosphere, taking measurements as it goes. The descent has 3 stages, with the first investigating the entire atmosphere. The probe will be looking at the composition of the atmosphere in detail, providing information on each layer as it falls. We know sulfuric acid is confined to cloud layers at around 50 kilometers or 30 miles up from Venus, and we know that the atmosphere is 97% carbon dioxide. But studying trace elements can provide information on how the atmosphere ended up in this state. The second stage of descent will be looking at lower altitudes to measure weather properties such as wind speed, temperature, and pressure in detail. The last stage of descent takes surface images in high resolution. While this is very common for Mars, it has always been a challenge on Venus. The thick cloud layer means visible light is reflected, so observing from Earth or from its orbit isn't practical. The intense surface conditions also means rovers are impractical. One suggestion has been a balloon mission. We have a low-resolution image of the surface of Venus, thanks to NASA's Magellan mission in 1990, which mapped the surface using radar. The Da Vinci probe will take surface images using infrared light during its descent. These pictures will not only allow for better planning for future missions, but also help scientists investigate how the surface formed. The second mission to Venus is called Veritas, short for Venus Emissivity Radioscience, INSAR Topography and Spectroscopy, again Veritas. This will be a more standard planetary mission. The orbiter will carry 2 instruments on board to map the surface, complementing the detailed infrared observations from Da Vinci. The first of these is a camera that observes in a range of wavelengths. It can see through the Venusian clouds to investigate atmospheric and ground composition. This task is very difficult, as the surface temperature causes the reflected light to have a very broad range of wavelengths. Veritas will compensate for this using techniques often used to study the atmospheres of exoplanets. The wavelength camera will also look for signs of water vapor. The Venus Express mission showed that the main elements escaping the Venusian atmosphere are hydrogen and oxygen, so if there's any water, it will be in tiny amounts or deep under the surface. The second instrument is a radar and utilizes a technique used extensively on Earth observation satellites. A very large active radio receiver, important for high-resolution images, is simulated using radio pulses pointed at different angles in front of the spacecraft. The high-resolution radar images will create a more detailed map to investigate the surface evolution of Venus, as well as determine if there is any tectonic or volcanic activity. These missions could also add evidence to a theory that the Venusian surface completely melted and reformed 500 million years ago. This came about to explain the lack of meteorite impacts on the surface, but so far no evidence has been found of a volcanic lava layer which could result from such resurfacing. So, it could be said that a much anticipated new decade of Venus science is at hand. However, there is another Venus exploration mission that is going to beat them all to first science return: the James Webb Space Telescope. JWST, through several of its observation programs, is going to be observing greater than 10 exoplanets that have been categorized as potentially Venus-like. The search for Earth-like exoplanets has, and will continue to reveal, more Venus-like than Earth-like worlds for the foreseeable future. Venus-like worlds are hotter, brighter, closer to their parent stars, easier to spot, and their cloudy atmospheres are easier to see and acquire spectra, which is one reason JWST is looking at so many compared to Earth-like planets. However, just like with our own Venus, that same quality makes it harder to understand what's beneath the clouds. Fortunately, we can quite literally get into and under Venus's clouds. Visiting our own Venus and studying it in situ gives us a significant advantage in understanding the composition and evolution of the atmosphere and the planet itself, and gives us a baseline for comparing with spectrally similar worlds outside the solar system. With Venus, we can explore and understand the detailed relationships between interior and surface processes, surface atmosphere chemistry, deep and upper atmospheric circulation and interaction, and planet-stellar environment relationships that define how the planet broadcasts its state to the universe in emitted, transmitted, and reflected light. We can predict how Venus itself would look to JWST from various distances in different orientations and observation configurations. We will present a JWST-like Venus spectrum, compared to that what we expect for exovenuses, and discuss how and why they may differ. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. And as always, thanks for watching, and we'll see you next time.